Bismillahirrahmanirrahim. Assalamu alaikum, students. Hope all of you are fine and in the best of your health and taking care of yourself and the whole family. Today, I'm going to discuss a lesson on physics topic, refraction. Physics code of this syllabus is 5054. It is basically for the class C2 and it is week 4. And we will start it with after discussing this following objectives. Number 1, in today's lesson, we will precede the process of refraction with the description of experiments to show refraction of light through glass blocks. Second objective is recall and use the equation sin I over sin R is equal to n. And third objective is define the terms critical angle and total internal reflection and recall and use the formula sin C is equal to 1 by n. Describe experiments to show total internal reflection. Describe the use of optical fibers in telecommunications and state the advantages of their use. So in today's topic, basically we will discuss the 3 and 4 experiments related to refraction of light, total internal reflection and critical angle. And then we will also see the different applications of total internal reflection in the use of optical fibers in telecommunications and its advantages. So first of all, we will have a quick recap of our previous lesson about the refraction. We have discussed the phenomena of refraction, the laws of refraction. The first law is incident ray, refracted ray, and the normal all lie in the same plane. And the second law we have discussed earlier in the previous lesson also, that is the ratio of sine of angle of incidence to the sine of angle of refraction is constant in any two transparent mediums, which is termed refractive index. And refractive index is basically, you can see we have discussed it many times, it is the ratio of sine of angle of incidence to the sine of angle of refraction here. Refractive index is basically a constant value of every transparent medium have due to the process, due to the bending of light. The more the medium denser, the more will be the bending of light and more will be the refractive index. For example, the refractive index of air is very less as compared to the refractive index of water and glass, because the more the denser medium, more will be the value of refractive index. We can see here in this figure also, when there is an incident ray of light incident on any medium, that is basically between the interface of two transparent mediums, that is air as a medium and water as a medium. When a ray of light enters from air to water, it bends. It is not preceding its original direction. Its speed decreases, and due to its decrease in speed, we have discussed earlier that the refracted ray, this ray is known as refracted ray. This ray is refracted ray. It moves towards the normal. So always remember, whenever the light comes from rare to denser medium, its angle of refraction is always less than the angle of incidence. And some part of the light is also reflected at the point of incidence. Where is the point of incidence, students? We have discussed the point at which it will strike the interface of the medium. That point is known as point of incidence, and that point at that point of incidence, well, we always draw a normal. Normal we have again discussed many times, a line which is perpendicular to any surface. Okay, next is about the speed of light in different medium. This is very important because we have discussed the process of refraction occurs because in the change of speed of light. As speed of light decreases in denser medium, and then when it goes in more denser medium, its speed also decreases. So how the speed of light changes depending upon the medium is, that is number 1, the speed of light in vacuum, and in vacuum there are no air particles. Speed of light is more and most in air or vacuum, that is 3 into 10 raised to power 8 meter per second. But when we talk about water, water is a more denser medium than air or vacuum. It has more number of particles per unit volume. So its density is high. The more denser the medium is, the less will be the speed of light in that medium. That is, it decreases to 2.26 10 raised to power 8. And when it comes to acrylic, that is a type of a glass, you can say, material. All these 3 mediums are shown in figure, that is vacuum or air, that is water, and acrylic, and it's 1.76 10 raised to power 8 meter per second. Okay, now the index of refraction, we have discussed it last time, but we will discuss it again. But before that, we will discuss an experiment related to refraction of light. For that, you have to see the video carefully, which I am going to share, and then we will discuss it later on. Okay, students, see this video carefully and you will understand very well about the refraction of light.
Refraction through a rectangular glass slab. Let us now perform an experiment and find out how light gets refracted when it is incident on a rectangular glass slab. Apparatus: a drawing board, rectangular glass slab, drawing pins, sheet of white paper, a protractor, and sharply pointed pencil. Procedure: let us consider a drawing board with a sheet of white paper fixed with drawing pens. Keep the rectangular glass slab in the middle of the drawing sheet. Mark its boundary, ABCD, with a pencil. Remove the glass slab. Draw an incident ray, IO, on AB. Draw the normal at point of incidence, NON dash. Fix two pins, P and Q, on the incident ray, IO. Place the glass slab within its boundary, ABCD. Looking from the other side of the glass slab, fix two pins R and S, such that your eye and the feet of all the pins are in one straight line. Look through the glass slab along the plane of the paper from the side CD and move your head until the images of the two pins P and Q are seen clearly. Closing your one eye, adjust the position of your head in such a way that the images of the pins P and Q lie in the same straight line. Fix two pins R and S such a way that your eye and the feet of all the pins are in one straight line.
I hope so, girls. This is very clear from this experiment. First, you will draw the boundary. Then you will fix two pins P and Q in a straight line at some angle with the normal. That angle can be 30 degree, 40 degree, 45 degree. And you will see the image of these two pins from the opposite side to that pins. That is, if you are putting those two pin sides towards the side AB, then from the CD side you will close your one eye and you will see from the other eye that the image of those two pins, then the image is such a way that the pins come in one line. It looks like instead of two pins, both pins are correct, inserted in same line, and they just give you the image of one. Then in that straight line you will put this third pin R, such that the image of P and Q pin and this R pin, they are in one line. Although from the apparent view they are not in one line, they are at different angles, but from the inside glass block they will be in one line, and in that line again you will put the second pin S also. So we'll continue.
Remove the slab and also the pins from the board and encircle the pin pricks on the paper with a sharp pencil. Join the position of tip of the pins P and Q and produce the line up to AB. Let PQ meet AB at O. Similarly, join the positions of tip of the pins R and S and produce it up to the edge CD. Let RS meet CD at O dash. Join O dash. It is a refracted ray. Measure the angle of incidence, angle I, angle of refraction, angle R, and angle of emergence, angle E, respectively. Angle I greater than angle R, and angle I equals to angle E. Also produce PQ up to P, as shown by a dotted line. The emergent ray is parallel to the incident ray. The above experiment shows that when a ray light is passing from air to glass, from a rarer medium to a denser medium, the refracted ray bends towards the normal drawn at the point of incidence. In this case, angle I greater than angle R. When the ray of light is passing from glass to air, that is, from a denser medium to a rarer medium, the refracted ray bends away from the normal. In this case, angle R greater than angle I. The emergent ray, O-E, which is nothing but the refracted ray emerging out of the glass slab, is parallel to the incident ray. This means that the refracted ray, emergent ray, has been displaced from its original path by distance xy. This displacement is referred to as a lateral displacement. Now, you're familiar with the refraction of light. Refraction is due to change in the speed of light as it enters from one transparent medium to another. Experiments show that refraction of light occurs according to certain laws.
So according to this video, it's very clear to all my students, I hope so, that the laws of refraction can be verified by this simple experiment, that the incident ray, the refracted ray and the normal all lie in the same plane of a paper. Secondly, the ratio of angle of incidence to the angle of refraction is known as equal to a constant that is known as Snell's law. Okay. Now we will continue that so that you can understood.
The following are the laws of refraction of light. 1. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. 2. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of refraction. If I is the angle of incidence and R is the angle of refraction, then sine I by sine R equals to constant. Equation 4. This constant value is called the refractive index of the second medium with respect to the first.